compensation of some mortality source, to me, that's not enough because you need to show how it occurs. Additive mortality is straightforward. You harvest them, they're gone. You don't need any magic to figure that out. But to harvest something and have it have no impact on a population, that's a little harder. And so I think the onus is on you to demonstrate a mechanism whereby that can happen. And a couple of mechanisms whereby that might happen. Probably the most commonly considered one is density-dependent feedback in a population. But another alternative is individual heterogeneity in a population. All individuals aren't the same. Some might be more vulnerable to harvest mortality as well as natural mortality. And if harvest falls disproportionately on those individuals, the consequences aren't going to be as extreme as they would if everybody's the same. So let's start with basics. And to me, this is very basic. I've taught this in Intro to FWCB and Principles of Wildlife Management. And, it goes back to the 1970s, at least. Anderson and Burnham, ideas of additive versus compensatory mortality. And I want to argue that there's only one parameter that's important for understanding the difference between those two relationships. And that key parameter is survival in the absence of hunting. I'll call it S0, natural survival rate. And curiously, for the species I work with, mallard ducks or any sort of waterfowl, we can only estimate survival by harvesting them because we need tag recovery. So you might say, if that's such an important parameter, let's stop harvest for a few years and measure it well. Well, we lose the ability to measure it in species where we rely on dead recoveries. So S0 is the intercept. There's another obvious point. If we harvest them all, they're all going to be dead. Survival will be 0. There's a straight line between those 2 points, and the slope of that line is also S0, negative S0. And so that's an important concept to wrap your head around, because some people think of additive mortality as if somehow hunters are able to only harvest those individuals that would have otherwise survived forever. And that isn't the case. Natural mortality and harvest mortality, if they operate independently, what you get is that the slope there is something less than 1. And 1 minus that slope is the proportion of individuals that get harvested, that if they hadn't been harvested, they would have died of natural causes. So there's some compensation that just happens by multiplying 2 survival rates together. For compensatory mortality, same intercept, and there's an inflection point, and S0 also determines where that inflection point is. The maximum amount of compensation you can get is 1 minus the harvest rate. And thereafter, if you go all the way out to that point, harvest is going to be incremental, the slope is going to be -1. And so S0 determines the boundaries here. It's important, if we're working on different kinds of species, to think about the implications of that. For a species with very high natural survival rate, and sorry, I'm an ornithologist, but put a lake sturgeon up there, put a, I don't know, female elk in her prime or something up there with a very high survival rate, there's not a lot of potential for compensation. On the other hand, if we're working with mourning doves or snowshoe hares or something, there's a tremendous potential for compensation. So if we want to understand how 2 mortality sources work, or 2 different survival probabilities work, we can think about survival, harvest survival as the probability of surviving harvest mortality. Often we think of mortality, I want to avoid saying rates because rate is the wrong word. Mortality proportions as being 1 minus the survival rate, and that's the proportion of a population that gets harvested. Better yet, to do what most of the fisheries world does and work with instantaneous mortality rates where we take the log of survival. We do the same thing with natural survival. 1 minus the probability of natural survival gives us the probability of natural mortality. Better yet, to do instantaneous, take the log of the survival rate. If we want to see the product of surviving two different mortality sources, they're independent, multiply the survival rates together, that works. Do not do this. Do not add the interval mortality rates together. And the term additive makes it sound like that's what you should do, but that is wrong. Anderson and Burnham got that wrong in 1974. In 2023, I still see people who get that wrong, working with, polar bears and things that are really important. Not gonna name any names, but yeah, don't do that. Don't do that. What you have to do is take a cross product here, and there's this right here. Sorry if you're on Zoom. I pointed to this little bit right here. There's a cross product, and individuals don't die twice. So you got to account for the probability that you would have died of both things and add those individuals back in. If you work with instantaneous mortality rates, you can just add them together, and it's beautiful and it's wonderful. And I'm a big advocate for working with instantaneous mortality rates. Now I want to point out that these two ideas, additive and compensatory mortality, are extremes along a continuum. In fact, you can go beyond the continuum and have super additive mortality and super compensatory mortality. I don't think it applies to the systems I work in, but it could. There are places. I gave a lot of this at a plenary talk in France, year-end presentation, and Jean-Dominique Leberton was in the audience, so that was a tickle for me to be able to do that. And he wrote a paper back in 2005 saying it is virtually impossible to have completely compensatory mortality in the system. It requires almost instantaneous density dependence, and nobody has ever observed density dependence that strong in a bird population in the wild. Maybe if we get into lifeboat economics where there's 20 of you on a boat designed for 10 and you have to survive in the North Atlantic for a month, you could have that kind of strong compensation. But he also pointed out in the same review paper that partial compensation can have a huge impact on population dynamics. And we don't have any models for measuring partial compensation, or at least we don't have any good models for measuring partial compensation. So my contribution to this idea of additive versus compensatory was stop thinking of it as either or and build models that are intermediate between the two. And to keep stuff in sort of the logical parameter space of that blue triangle, I built broken stick regression models that can be constrained to occur within that parameter space. And I mean, that's still a little bit arbitrary, and I'd love some smooth, functional, continuous curve that stayed within that space. But for now, at least, I think it's an improvement. So to see if such models could actually work and estimate the proportion of mortality that was additive or compensatory, I did simulations, because with simulations, we know what the truth is. The truth is the parameters we designed. And so a simple approach would just be to use regular models where we estimate survival and harvest, and after the fact, look at the relationship with a regression, sort of post hoc. We can use the pure additive model. We can use an additive model and include random variation in annual natural survival. And so we've got a lot of lines that aren't quite in parallel, but they're all converging towards the same point of after we kill them all, they're all dead. Some folks have used models that look at a process correlation between a harvest rate and survival. And if that process correlation is strongly negative, that suggests additive mortality. If there's no evidence of a correlation, it suggests things might be compensatory. Here's the compensatory model with no annual variation in natural survival. Here it is with natural variation in annual survival. And here are three new models that came up with it. To best of my knowledge, nobody has used before in this sort of scenario. One is to work with instantaneous mortality rates or hazard rates and look at correlations between natural survival or natural instantaneous mortality and survival from hunting or harvest instantaneous mortality. And what you're seeing in this case, this one has different axes because natural survival goes up as harvest goes up. That suggests some sort of compensation is occurring. If natural survival would stay flat with increasing harvest, then the combination of the two would lead to increasing mortality. Broken stick models with no annual variation, broken stick models with temporal variation in natural survival. So I simulated data with known properties, and through those data at all 9 of these models, I want to ask, how well do they work? And here's an example of output from one model. And what you can see in red, the red line is the true functional relationship. The red dots are true annual estimates with some variation around the true functional relationship because of variation in natural survival. And black are the point estimates from different models. And when the true model isn't additive or compensatory, sort of down the middle column, the models are awful. Any model that allows for some intermediate level of compensation can kind of get the functional relationship pretty good. What I point out here is if you look over on the rightmost column, when we add random effects to additive models and the additive function fits poorly, I'm a big proponent of random effects and analysis. And if you're a grad student, then I'll say, why don't you use random effects? Random effects can do some awesome things, but this pointed out to me that they're a double-edged sword because they can allow a really inappropriate model to fit the data very well. And you just reach out and explain the points. And so that's what you're seeing. Far right top panel and far right middle panel. Okay, so this is one example. I did hundreds of examples. And how well do they work? How well do they work for estimating S0, survival in the absence of harvest? Remember, that's the critical parameter. A lot of models do really well. Additive models always overestimate S0. Compensatory models always underestimate it. If you're at all familiar with harvest management in North American waterfowl, they do something called adaptive harvest management. They've been doing it since 1995. They're writing papers about it as if it's the best thing in the world. And why hasn't everybody else followed us down this corridor? And it's a choice between the worst model and the penultimate worst model. Neither of them are any good at all at explaining what's going on. It's not just this parameter. How well do we estimate annual variation in natural survival if it exists? All models overestimate it, but additive and compensatory models severely overestimate it. Most models do pretty well at estimating the annual survival rates, if that's important to you. But the new models are better than the existing models, so I was pleased to see that. We do even better estimating harvest rates, so we can estimate harvest rates with greater precision than we can estimate survival rates. How well can we estimate the tipping point? there's a tipping point where you have a high degree of compensation and then it changes and there's less compensation. That could be an important, reference point maybe for a harvest rate. You want to stay under the tipping point. We do pretty well unless the tipping point is really small. And what I point out is if the tipping point is less than 0.05, where we're missing the boat here, there are only 5 or 6 data points, less than 5 or 6 data points to estimate a break to the left side of the equation. So it's almost irrelevant if it's that close to the edge, I would argue. How well do we do? To me, this is the most important one, and this is where I was disappointed. How well can we estimate the proportion of mortality that's additive during that first segment? And we tend to overestimate it when it's small and underestimate it when it's large. The improved models do better, but I'm not going to argue that that's good. Thinking about this a little bit more, if you're familiar with Bayesian approaches at all, they require priors. And my priors here are brick walls at 0 and the maximum. And so if you throw something at a brick wall, it bounces off and it's not going to end up close to the brick wall. I'm thinking I need to redo this analysis with priors that allow the estimates to wander outside the logical space. And maybe they'll do better. But that's my disappointment so far. This part doesn't work as well as I'd like. Okay, if you demonstrate that there seems to be compensation of harvest, I think the onus is on you, the manager, you, the biologist, to provide evidence for a mechanism whereby that might occur. And one of the most commonly suggested ones is density dependence, that when populations are high, survival rates are going to be lower, fecundity is going to be lower. I don't think like a fish ecologist, but somatic growth rates can be lower too. And if you're measuring biomass instead of numbers, that might be the way in which we see compensation. So a couple of things that I think are important for looking at how. I don't think you can just do it from comparison of harvest rates to survival rates. You need more information. That's where integrated population models come in. And I've really become an advocate for using instantaneous mortality rates or hazard rates. If I ever do another survival analysis with logit links, call me on it. I need to do something better than that. So this is a paper that recently came out. I'm co-author on it. And my claim to fame on this is that I pushed Thomas, you need to use hazard rates instead of survival to look at this. This is an integrated population model. One of the problems with integrated population models and lots of parameters is you kind of run out of Greek letters. I don't expect you to know what any of that means. I can't follow it myself. Let me put labels on it that are a little more meaningful to me. And what the analysis showed is that kind of everything affects everything to some extent. And if we're thinking about a harvest system, we have to realize that population size of the species we're harvesting influences how many people want to harvest it. It influences the regulations we have, but the regulations don't just influence the harvest, they influence, am I going to buy a duck license this year if I live in Maine and I can only shoot one black duck? Maybe not. And so there's a lot of feedback here, but one of the feedback loops is how population size affects vital rates, fecundity, harvest mortality, and natural mortality. And for vital rates outside the hunting season, for 2 out of 3 variables, there was compelling evidence of density dependence acting in a direction where large populations would have lower growth rates. So fecundity was density dependent. Adult female mortality was density dependent. We found no evidence of it for juvenile mortality. I think we can get a better idea of what's happening with population dynamics if instead of looking at annual rates, we break annual cycles down and look at different seasons. And this is a cool paper on birds in total, Dr. et al. It's using weather radar to measure the cross-sectional volume of birds crossing. Think of it as a picket line of points across the southern United States. And so they don't know which birds, but they can measure how many birds went past in the fall, how many birds came back in the spring, and they can also look at long distance migrants versus short distance migrants. And from that, they calculate cumulative mortality across the entire guild of short and long distance migrants. And they were surprised that long distance migrants actually survive winter better. Yeah, they go all the way to South America, but I don't know, to get away from North American cats or something, I don't know. But why aren't short distance migrants declining precipitously relative to long distance migrants? Well, from the same data, they can get a recruitment rate between spring and fall, and the recruitment rate for the short distance birds is bigger than it is for the long distance birds. They arrive earlier, they've got time to double clutch and things like that, so they can produce more offspring. Similarly, if we can mark animals at multiple times per year, instead of traditionally what we've done in the waterfowl world is we put bands out right before hunting season because that's what we want to measure. But if we put bands out right after hunting season too, we can measure survival during the hunting period, and we can measure survival during the non-hunting period and figure things out much better. So the population model looks something like this, and I just want to show that that by breaking things down, we can break survival into a winter component and a breeding component. We can measure fecundity during the time period when it occurs, and then we can look for impacts from specific seasons. And this is a model I built a while ago for American black ducks. And just for giggles, I used instantaneous mortality rates and instantaneous fecundity rates. And now I think that's the way to go at it. It's a better way to go at it than trying to look at survival. So what you're looking at here is population of adult female black ducks with a time step of 6 months. And so the increases are due to recruitment. There's also some mortality that occurs there, and it's recruitment plus mortality that occurs in that time step. The decreases are during the wintering period when there's no recruitment, and so it's just mortality losses. And that's what a population in a seasonal environment looks like. It's seasonal. It goes up and down like a yo-yo or a sine curve. The harvest management world in waterfowl is big on yield curves. And that's a way of showing off that at least you understand what a first derivative is. And if you take the first derivative of a logistic growth curve, you get a yield curve. But I don't know of any populations that grow like a logistic growth curve. They wax and they wane, and they wax and they wane. This is more like a sine curve. You take the first derivative of a sine curve, you get a sine curve. Take the second derivative of a sine curve, you get a sine curve. It's sine curves all the way down. Maybe it turns into turtles at some point, but we need different models for populations in a seasonal environment than logistic growth. Even in a fish world. I mean, and if you're doing biomass instead of numbers, you're getting almost no somatic growth during the wintering period. You're losing individuals. You're getting gains in somatic growth and recruitment during other time periods of the year. So that's what the equations look like. You don't have to, I'll walk you through an equation in a bit. The equations are important. Not only should we work with instantaneous mortality rates and instantaneous fecundity rates, but we should work with the logarithm of population size, not Excel's logarithm, the base E logarithm, R's log. And the reason for doing that is because if we have an instantaneous mortality up there, the top line, log of adult female population size post-harvest is equal to the log of the population size before harvest minus the instantaneous mortality rate from harvest. And that is the difference now in population size. And just to rearrange it, adult female harvest represents a change in log abundance that occurs as a result of harvest. And how big that change is important. That's the effect size that we'd need to see on other parameters in order to have density dependence explain complete compensation. In the past, we've just seen, well, there's evidence of density dependence. Good. Is there enough density dependence to overcome the harvest mortality? And so what it would look like is that if we plot any vital rate against change in log abundance, we need to see a slope of 1 or -1, depending on whether we're looking at mortality or fecundity. And initially for black ducks, I had weak evidence of that adult female summer mortality was density dependent, but it's nowhere near strong enough. And it would have to be as strong as the red outline there in order to explain what's going on. And we get no help from fecundity whatsoever. And so in this system, density dependence doesn't appear to be strong enough to overcome the harvest. What I'm working with on the x-axis here, though, is change in population size of adult females. What's the right population size to have on the x-axis if you're looking for evidence of density dependence? In the past, if we're looking at juvenile male mallard survival, people have always looked at juvenile males. Well, juvenile males don't just compete with juvenile males. They compete with adult males and adult females and juvenile females. And something else I'm working on in waterfowl, and I'm going to be presenting on this spring, is sex ratios, adult sex ratios of North American waterfowl are getting seriously out of whack. If you've had me as a student for analysis of populations, you know I've heard of male ducks as sperm bags with wings. Adapt that for whatever critters you work on. I won't say they're unimportant, but ducks are kind of monogamous for 12 seconds, and that's about it. And they're not essential for anything in terms of biparental care. And if the sex ratio is getting this out of whack, and all these individuals are competing for resources, maybe that's a concern in terms of survival of adult females, survival of juvenile females. And we ought to be looking for evidence of that. In the waterfowl world, we harvest multiple stocks, multiple species of duck. And how do they compete with each other? And so what's the relevance of does half a gadwall equal a mallard in terms of competition? And when we have multiple stocks and we're managing for multiple stocks, understanding density of other species might be important. Predator prey switched around. It's what's the density of all the things that eat elk. So I'm intrigued by this. And I think the way to get at it is through integrated population models that can explore these relationships between population size of what, I'm not sure, more than just the cohort of interest though, and the vital rates for that cohort. Finally, a little bit about another potential mechanism for compensation of harvest. What role might individual heterogeneity play in demographic compensation? 20 years now ago, Shirley Pledger came up with models for market recapture data that instead of making the unrealistic assumption that earlier models made that every individual in the population has the same probability of survival and the same probability of encounter, which understandably is why no evolutionary ecologist has ever gotten interested in market capture models, because they sort of start from assumption one, Darwin was wrong, everything's the same. Well, Shirley Pledger came up with the first step of models that got away from this. And there's a classic data set if you do market capture work on European dippers. If you want to build a better live encounter model for survival, you have to fit it to this data set. So Shirley fit it to this data set instead of getting an estimate of mean survival that applies to everybody. She estimated that there was a huge contingent of individuals that had survival nearly that high, a little bit higher even, but some individuals that had really poor survival. These are live encounter data, so those could be individuals that moved away from a study area and never came back. It could be permanent emigration. If you work with dead encounter data, you have to fit your new model to the San Luis Valley Mallard data set. And she fit her model to these data. Instead of one survival of 65% for adult males, she found a contingent with very low survival. And here, because these are dead recovery data continent-wide, it's true survival. It's not emigration. So I'm going to call those groups in the leftmost, I'm going to call them a doomed surplus, call them a walking dead, whatever you want to call them. And I'm going to suggest that they're free to harvest. They wouldn't survive anyway. If you could figure out how to harvest those individuals, they're free for the taking. So I got dead recovery data for 12 species, mostly hunted species. I threw in red-winged blackbirds just because there was enough data on those as well. Some cases there was data on males and females, so I had 16 data sets. And I found statistical evidence of a contingent of the population having near zero survival in all of the species outlined in a red box. And so to me, that's evidence of what Arrington would have called a doomed surplus at the right before hunting season starts. What are the consequences of having a doomed surplus in a population? Well, if those are the individuals that you tend to harvest, the consequences of the population might be pretty slight. I'd almost guarantee from everything I read, but I'm looking at you, Joseph, and you, Jack, that wolves are harvesting primarily the doomed surplus in populations of ungulates, the ones that are slower than everybody else. They're running after a herd of elk. What do the consequences look like for harvest management? This is a complex slide, but let me try to walk you through it. And there are two different regressions shown for each species, and these are examples where there was evidence of a doomed surplus. So the dashed line has a y-intercept, which is also the slope, take the negative value of it, of what you get if you assume all individuals in the population are the same. The solid line with the two different numbers are what happens if you recognize the population as a mixture of hardy individuals and frail individuals. First of all, baseline survival in the absence of harvest is a lot lower than you think it is. The slope is also much shallower, meaning there's a fair bit of compensation that occurs because of heterogeneity. And this occurs even without differentially targeting the individuals that are most frail. In fact, a model that allows differential targeting of frail individuals is not identifiable. So I kind of have to do thought experiments about, can you imagine scenarios where they might be more harvestable? I think about hunters harvesting ducks. Who do you harvest? You harvest the dumb juvenile that comes into your decoys and my bad duck calling, and they're probably part of the doomed surplus. If you're sitting on top of a hillside with a 7mm Magnum and a big scope and picking out the biggest elk you can find, then maybe not. Maybe it might tip the other direction. So it depends on the correlation between the two. The correlation between the two in these models isn't estimable to the best of my ability. So where are we? I've not answered very many questions. I've asked a lot. That's a good thing to do before you go out on sabbatical. I think there are a lot of unanswered questions to me, but this is an area where I want to invest work going forward. One of the things I really want to do in that model set of 9 models is come up with something that's a continuous function instead of a broken stick. Conversations with a postdoc in Wisconsin who isn't supposed to be working on side projects, so I won't rat her out. But we're gonna do something along those lines. I'm really interested with density dependence of trying to get at population size and what are the populations that matter most in terms of influencing density dependence. I've done analyses on 11 species of North American waterfowl now, and in every case, there's an increasingly male-biased sex ratio through time, going back to the 1960s. So that can't be good for a population. It provides some harvest potential, but also understanding why it's happening. It's not happening because of harvest. I'm interested in doing that. The bottom bullet point is the most difficult one. Models that can handle heterogeneity in binomial processes are really difficult to work with. They're difficult in the human biomedical world where we have perfect information. Throw those sorts of models at individuals where you put out 100,000 bands and 90% of them are not seen again is even more problematic. So that's what I have. I'd love to entertain any questions if anybody has any. Go ahead, Ken.
So, I mean, of course, I do phylogenetics, right? Which is a little bit different than this, but we're interested in growth rates through time. Instead of like looking at, say, populations, we look at like species or lineages. This is kind of a really big thing in the phylogenetics literature for at least more than the last decade, like density dependence. You mentioned something like, and a lot of like arguing that goes on, it's like, well, you can have like a pure birth model, say, for example. If you add extinction into it, you get what's called like the pull of the present, you know, only, the pull of the present. So you get kind of a upturn at this is plotting the number of lineages through time, right? On a time calibrated tree. So you get the pull of the present because those lineages haven't had enough time to go extinct yet. So you're still observing them. So it looks like there's an uptick in the birth rate. And then there are these issues about like, you know, the constant birth model. You talked a little bit about the sigmoid model there, but over time, like how does this average out like over time? I'm just wondering. I mean, I'm thinking about like a longer term perspective, but at one point, like, I mean, I could see how these models maybe parameterizing these ways under like certain windows of time will provide you a better estimate. But as you stretch them out over longer periods of time, say to like, you know, looking at birth and death rates of populations over hundreds or maybe thousands of years, maybe a lot of this averages out, and so a simpler model does fit. I'm just curious what your perspective is on that.
I mean, when you add time to the equation, you almost have to have density dependent population responses, because if you don't, even a very slightly negative growth rate over hundreds of thousands of years leads to extinction and they're gone. Even a very slightly net positive growth rate over 100,000 years is, the Star Trek Tribble episode where everything's covered up to your eyeballs and beyond. And so, from that argument, you almost need to have density dependent, but I don't want to be in a position where I have to say, well, we need it like that, building this argument. I want to find evidence for it as well from empirical data.
There's a really big argument right now, like in phylogenetics, the growth of lineages over time, whether there is density dependence. There's like a species packing, a maximum number of species that you can say fit into a region or a community, and that you see a decline, in the birth rate over time. So that kind of matches with your perspective, but there are lots of other confounding factors that we argue about that are beyond like this discussion. So I appreciate that perspective that over any length of time you do have to start accounting for density dependence. And we've argued about this for a while in phylogenetics, whether it was inability to count recently evolved lineages that leads to the decline over time, or whether it's something that is actually really real. And the data, I think, are starting to say that over appreciable amounts of time, there is evidence of density dependence of the number of species or lineages that can fit into an area over time.
So sorry if you're on Zoom, but you might not have heard the question. I should have repeated it, but it was about these sort of consequences in the fossil record through time with species extinctions. And a question for you, Ken. Inferences about extinctions, are those coming from the fossil record or
in some cases they do come from the fossil record. In some cases there are neontological estimates of them by looking at the shape of time calibrated trees over time and trying to estimate instantaneous birth and death rates at particular points based on the number of lineages that have survived to the present. So a combination of both.
Okay. Yeah. If it is fossils, it's sort of enters in some of the stuff we deal with in mark recapture of sort of imperfect detection of a lineage that went extinct and something like that. You're undercounting what was really there probably in the fossil record, but are you consistently undercounting, or might that have changed through time? Yeah. Anybody else on Zoom? Go ahead, Joseph.
When I think about individual heterogeneity, all I can think is what other
yeah, and for the most part, this is latent heterogeneity. It's not something that's obvious at the time of marking, but it's something that if it's real, it's not an artifact. This animal I just put a marker on is part of a doomed surplus. I don't even realize it. Body condition is something that I wish we measured more often. Better understanding of capture myopathy, and that would be the thing you hope it isn't, but it could be something like that. Just capturing and handling stuff. What they've learned from marking geese up in the Arctic is that catching a lot of geese at once and holding them and taking 2 hours to process them, those cohorts will have lower survival than individuals that get processed more quickly. And so that's part of it, though, I think, is sexual recombination. Here's a project for you to design a species that has twice the growth rate of an existing species. Easy, turn on parthenogenesis. But good.
things that I'm would be genetics, and you could probably also assess body condition doing that. So that might be interesting to do assess the effects that or on good selection, what kind of effects on good selection.
And for the benefit of Zoomers, the comment was about white-tailed deer harvest and the impressive amount of information you can get on harvested individuals. Maybe then to look at, are they different from unharvested individuals? Would require some alternative way of sampling and collecting info on the non-harvested ones. And the game hunters have the ability to differentiate. Most people will avoid fawns, for example, but in the waterfowl world, juveniles are most vulnerable to harvest. You can't tell at the time that something is circling, coming into your decoys for the most part, if it's a juvenile or not. And so the most vulnerable are the ones most likely to get harvested. Whereas if you're a white-tailed deer hunter, you might pass those up unless it's your last day and you really want to bring home some venison.
So a little more off topic, but you made a really good point. I agree with you. Seems like in the public, it need to be. Curious, like, why do you think that is that popular understanding?
Yeah, I think we need simpler ways to explain it, but to use wolves as an example, in my lifetime, now granted I was wee little, but in my lifetime in Minnesota, there was a bounty in wolves in northern Minnesota. There were still wolves in northern Minnesota, and you couldn't wipe them out despite a bounty, and absent harvest, range limits are growing, but population density per se hasn't gone exponential. And so I don't know. We need to come up with ways to explain to the Grand Rapids Whitetail Deer Hunting Association or whatever it was that these sort of processes are happening. But we also maybe need to explain it to the non-hunting, non-angling public that just because we harvest, a bunch of whitetails or, Lord forbid, a bunch of mourning doves when Minnesota came up with a mourning dove season, it has almost no effect on the population. And other sorts of anthropogenic mortality that we get worried about that I've played around with. Tower collisions for birds kills 7 million birds annually. Well, compared to those numbers I showed of how many migrate south and how many come back, 7 million is less than what we harvest of mourning doves in a given year. And we do that sustainably. And so there can be a lot of mortality without it having any impact. I don't think we should get complacent, though. We should look at new mortality factors and ask, does this operate in an additive or a compensatory fashion? Yeah.
Before I leave this, kind of like you're saying, it really seems to rest when they're carrying it fast, right? So what's going to be density going, which could vary, right? Through space, time. So what would once been considered, say, like whitetail deer, where they would have reached a point of density, you modify the landscape and have such a change and carrying capacity. So see density.
Yeah. Yep.
Change over time, right?
Yeah. I mean, to make a beautiful logistic curve for me to do in R or Excel. I specify carrying capacity, I specify growth rate, and I get that beautiful logistic growth curve by pretending that carrying capacity doesn't change for the 100 years or whatever it takes to get up there. But carrying capacity does change. For some species that depend on dynamic resources, it probably flops around like a fish in the bottom of a boat going up and down. Waterfowl, pond abundance on the prairies. It's dynamic. And we need to stop imagining that there's this beautiful line in the sand, K, that's remained inviolate for decades, if not centuries. If we have some idea maybe of what the key resources are and we can measure them, that could maybe be a proxy for how K might vary through time. I absolutely agree with you. We need models that stop recognizing K as a constant.
So this kind of comes back to the nuances of the whole portion. You thought about, or do you know ways where people have incorporated shifts in animal behavior throughout, say, a lifetime? These sorts of models, like for instance, individual shifts from using migratory strategies to partially migratory or not particularly, how that maybe influences different sources of mortality, or changing through time, whether they're in their prime, they might focus more on reproduction and finding available food, and then after that they may shift to avoid predation risk as they become more susceptible.
Yeah, I don't know of any good examples that do what you suggest, Jack, but I can think of really good examples from behavioral ecology world where all individuals aren't the same, especially if we have a complex social structure. How do you get super additive mortality? Take out the matriarch in an elephant herd. Take out a dominant male in a species with infanticide, and you take out more than one individual. Take out alpha pair in a wolf pack. So the work you've done, Joseph, and been involved in. And so, the consequences of removing an individual are more than that individual based on social structure. I think that's a very clear case where there's some really excellent examples of seeing that sort of an effect. In terms of changes with stage structure, I can't think of any off the top of my head. All right. Well, thank you, everybody.